Alright everyone, so I'm going to record a new installment in the differential geometry series, and this video is going to concern surface area, isometries, and the first fundamental form. So, to begin, let's go over this definition. So suppose we have a regular surface S and a subset R of S. So I wrote down a lot of words, so let's kind of unpack what I wrote. So R is a polygonal region if R is covered by a single chart from an open set U in R2 to S, and the inverse image of R is the interior plus boundary of a piecewise regular simple closed curve in R2. So let's say we have R2 and then maybe we have like a surface kind of like that, which we'll call S. Maybe we have an open set U, and it is mapped by sigma to maybe this part of the surface. Let's think about what a polygonal region might look like if we go backwards. Let's say we have a piecewise regular simple closed curve in R2. So maybe something like this. And this is the interior plus boundary of it. So we got that. This might be perhaps mapped to, like, I don't know, maybe something like this. Maybe it might be mapped to something like that. And that's R, and this is the -1 of R. You can see how R is sort of looks polygonal, right? So it's basically the image of a piecewise regular simple closed curve, its interior and boundary, as you can see here. So with that being said, we continue on. So now we're defining the surface area of R, which is over here. So that's going to be equal to the double integral over this region, this inverse image of the polygonal region, of this, oh, and this is known as the area distortion. And if you don't remember what the area distortion is, you can go check out my previous video. So basically, you can think of it as like taking all the area distortion at each part of this region and summing it all up. The area distortion from here to there. And that's basically what it is. You can kind of see how this makes sense intuitively, because like if the area distortion is 1, then nothing's really going to change between this polygonal region and or this polygonal region and its inverse image, like intrinsically. So that simply so the integral then would simply amount to adding up all the bits and pieces of this inverse image. However, in many cases, the polygonal region may differ from this by a factor of area distortion, and therefore this expression becomes a little bit more complicated. Now we can do a little bit more than just define area with these sorts of double integrals. We can also do the following. So if we have a function on our polygonal region, like maybe f is like, maybe it's like 4 here, maybe it's like 2 here, -1, then we can, instead of, just sitting there wondering how we can possibly integrate over such a convoluted shape, we can make it slightly simpler by simply defining it as the integral of the function. Let's say we have, if the integral of the function f composed with sigma multiplied by the area distortion times dA over the inverse image of the polygonal region. So now you're calculating, now you're summing up with respect to the inverse image, which is usually a lot simpler than, this, because over here you're working in 3 or potentially more dimensions, and everything's curved and you have to account for that. But here we're in R2, which is Euclidean. So that's a little bit about that. So now let's discuss a proposition. So our proposition is that the above definition is well defined. So that sort of means if we have 2 different surface patches that both cover R, then the integral of this should be the same in both cases. Now we're not going to prove it yet, but we need a lemma first. So we need perhaps a tool to help us before we begin proving. So if we have a diffeomorphism from open sets in R2, U1 to U2, and we have a polygonal region K, which is a subset of U2, polygonal region, then this expression holds true. Now, this might not look very familiar. This might look rather scary, in fact, but what we're trying to say is basically the following. So if we have, let's say we have a polygonal region. Let's make it a triangle. Okay, and we have open sets U1 and U2, and there's a map between them from U1 to U2. If we consider the inverse image, which might be, this is psi negative 1k, the integral of, maybe there's a function, oh no, it's the integral of a function phi, which takes a point in k and assigns to it a real value. If you do the integral of that, that's equivalent to the integral of this function, phi composed with psi, times the area distortion of the diffeomorphism. So there might be some area distortion, and we're looking at the pre-image of k. So we're summing up all over here. So this might look similar to like the change of coordinates rule you've seen in multivariable calculus. If you've taken that, that's because it's basically the same thing. It's just more abstract here. So let me box that in. And let's get on with the proof. So let's say we have a map psi, which is sigma 2 inverse composed with sigma 1. Remember, sigma 1 is applied first. So this is technically a diffeomorphism from the pre-image of the intersection of v1 and v2 to the pre-image of the intersection of v1 and v2, and sigma 1 and sigma 2. But for this case, let's just assume that v1 equals v2. So we're just looking at a diffeomorphism from u1 to u2. So we can see here that sigma 1 equals sigma 2 composed with psi by the fact that you can see here. And the chain rule gives us the following. The area distortion of the map d sigma 1 is equal to so this is by the chain rule. So remember, you take the derivative of this, the outside, and then you compose it with the derivative of the inside. And then there is something that we need to think about, and that is the following. So we actually have that if we have linear perhaps, I guess, isomorphisms, then the area distortion of F composed with G is going to be equal to the area distortion of F times the area distortion of G. And the reason why we have that is because if you let's see if I can prove this on the fly. Okay, so by the definition of area distortion, we have this, and it does not depend on the choice of basis, so V1 and V2 can be whatever. Now, I guess, oh, yeah, I see. Okay, so let's say that we have vectors g of v1 and g of v2. Then the denominator has to be g of v1 times g of v2 by the definition of area distortion. Furthermore, if we have vectors v1 and v2, then the area distortion of g is going to be g of v1 times g of v2 over v1 times v2. Therefore, if we multiply both the numerator and denominator up here by the absolute value of g of v1 times, or the magnitude of g of v1 times g of v2, and then do the same thing here. And of course, don't forget v1 times v2. This is going to be equal to the area distortion of F times the area distortion of G. So that sort of thing is proven. So now that we've proven this claim for sure, let's go back to the original proof. This we're going to split up like so. So we have that, okay? Therefore, now let's consider the integral of function f over r, which we have defined as the following. This is just by the definition of our definition of integration. Furthermore, by the change of coordinates rule, we have that this is equal to oh wait, no, this is not by the change of coordinates rule. This is by expressing sigma 1 as sigma 2 composed with psi. And then remember that we have this, d sigma 2, the area distortion of that times the area distortion of d psi is equal to the area distortion of d sigma 1. And therefore, by the change of coordinates rule now we're applying it, this is so now we're applying psi to the negative 1 times d. And I'm not going to prove this rigorously, but I think it should be fairly intuitively obvious that these two cancel out. Like, those two are going to be inverses of each other. And therefore, we see that this is precisely the definition of the integral just for a different coordinate chart. And therefore, these two definitions coincide with each other. And because these coordinate charts are arbitrary, we can therefore conclude that the above definition of integration on a surface is well defined. So that means the integral has the same value no matter which surface patch you use, so long as it's applicable. So let's move on to another proposition. So what I just wrote is the following. So if we have a function from a regular surface to a regular surface, S1 to S2, and R is a polygonal region of S1, then f of R is also going to be a polygonal region, and the area of f of R is simply equal to the double integral over R of the area distortion of df. So suppose we have a surface patch that covers R. Then f of R is covered by the surface patch F composed with sigma, which takes us from U to S2. Now, we just went over something similar, but note that we have d of f composed with sigma equals df composed with d sigma, which, as I proved before, like right on the fly, is equal to that. Therefore, by our definition of area, we have that is equal to the integral of the area distortion of D of F composed with sigma all over, over sigma, the inverse of sigma of R, which, as we stated beforehand, is equal to that, because this. And by the change of coordinates, we have and then we get double integral over R of the area distortion of dF, and that is our desired result. So that theorem has been proven. So now let's discuss just two more definitions before the video ends, and that'll basically be it. So now let's discuss the first fundamental form is a map from the tangent plane to R, and we basically define it, we map a tangent vector x to the squared norm of x. So you might be wondering what that p is doing there. That's basically showing that the vector x emerges from the point P. So that's basically, let's draw this out. So we have a surface S, and then maybe this is P, and this is TPS, the tangent plane. If we have a vector x, the first fundamental form takes us from x to, and then if this is, oh, that's a bad drawing. This is length, magnitude of x, and this is the magnitude of x. You can think of it as sort of like that. It maps from a tangent vector to its squared norm. So that's the first fundamental form. And the last thing that we'll discuss here is an isometry. So isometry. So if we have a diffeomorphism from S1 to S2, where S1 and S2 are regular surfaces, then F is an isometry if dF preserves the first fundamental forms. So that means the norm, the squared norm of x at the point P is equal to the squared norm of dFP of x at the point F of P. So what that sort of means is, let's draw this out. Let's say we have two surfaces S1 and S2, and there's a point P, and there's a vector x, so P and x. Maybe it's mapped perhaps over here, and maybe x is mapped here, so this is F of P, and therefore this is dF of P x. And we say that this is dF of P because we're taking the tangent plane and mapping it to the tangent plane of F of P of S2. So this is dFP. And of course the surfaces, the mapping between them is F. So I know this is like a lot to think about, but hopefully this visual diagram should give some sort of clarity. Now, an equivalent definition is that if we have x and y, which are tangent vectors at point P, and we have the inner product between them, that's basically equivalent to the inner product at F of P of this. Now, the notation I know is confusing with all the subscripts and P's and F of P's, but hopefully you can see the reason why they're being used. So if there exists an isometry between S1 and S2, then they are called isometric. And a measurement is intrinsic if it is preserved by isometry. That is, if we have an isometry between two surfaces, the measurement remains the same. Now, interestingly enough, I'm not going to prove this, but if we have a rigid motion F of R3 and S is a regular surface, F of S is also a regular surface, and F is an isometry between them, or the restriction of F to S is an isometry between them. So that's going to be it for today. Hopefully this was a helpful video, and I'll see you guys in the next video.